Imagine holding a bar magnet that can pull iron filings from across a table, or feel the invisible tug that keeps your phone's compass pointing north. Today we Eurostrade LL peel back the curtain on magnetism, Euros exploring how moving charges create fields, how electron spins generate tiny magnets inside atoms, and why these microscopic forces manifest as the powerful forces you see in everyday devices. A magnetic field is a region in space where magnetic forces act on moving charges and magnetic dipoles. When a bar magnet is placed, the field lines emerge from its north pole and loop back into its south pole, forming closed paths. The density of these lines indicates how strong the field is at any point. Closer lines mean a stronger influence. A small probe with a north pole will feel a push away from the source magnet at Eurostrade's north side and a pull toward its south side. This directional behavior shows that magnetic forces are vectorial, having both magnitude and direction determined by the field orientation. The force on a moving charge is given by F equals QV A tilde, B, where V is velocity and B represents the local field strength. Even neutral objects with internal dipoles experience torque, aligning their north pole toward the external field of Eurostrade's south side. This alignment explains why compasses point north. The Earth itself behaves like a giant bar magnet with its magnetic axis tilted relative to rotation. The field extends far beyond the visible magnet. It can influence electrons in circuits, generating electromotive forces when it changes over time. Understanding these mechanisms allows engineers to design motors, generators, and magnetic storage devices that rely on predictable field behavior. Pause 0.8. In an atom, electrons move in defined orbitals that carry angular momentum. This orbital motion creates a tiny current loop, which behaves like a microscopic bar magnet. Additionally, each electron possesses intrinsic spin, a quantum property that also generates a magnetic dipole moment. The direction of the spin of Euro's induced moment is fixed relative to the electron of Eurostrade's angular momentum by the land A tilde copyright Ga Euros factor. When many atoms are present, their individual moments can align through exchange interactions in certain materials. In ferromagnets, these aligned moments add coherently, producing a strong net magnetic field that extends beyond the material. Paramagnetic substances have moments that tend to align with an external field, but cancel each other when no field is applied. Diamagnetism arises from induced currents opposing any applied magnetic field, resulting in a weak repulsive effect. The collective behavior of microscopic moments explains why everyday magnets can attract or repel objects at macroscopic scales. Thus, magnetism originates from the fundamental quantum properties of electrons and their cooperative interactions within solids. Pause 0.8. Magnetism arises from electron spin and orbital motion, producing tiny magnetic moments in atoms. When many atomic moments align, the material exhibits a net magnetization that can interact with external fields. Diamagnetic substances possess paired electrons. Their induced magnetic moments oppose any applied field, causing a weak repulsion. Paramagnetic materials have unpaired spins that align partially with the external field, resulting in a modest attraction. Ferromagnets contain domains where electron moments are already aligned. An applied field expands these domains, producing strong magnetization. Graphite is a classic diamagnetic example. Its layered structure forces electrons into closed loops that generate opposing fields. Aluminum, with several unpaired Euros electrons, displays paramagnetism. It weakly attracts magnets but loses the effect once the field is removed. Iron exemplifies ferromagnetism. Its crystal lattice supports spontaneous alignment of spins, allowing it to retain magnetization after removal of an external field. In Acidia Euros B a Euro side chart, each materiala Eurostrade's magnetization curve shows the relationship between applied magnetic field strength and induced magnetization. Diamagnetic curves slope negatively, indicating that increasing external fields produce decreasing internal magnetization. Paramagnetic curves rise steeply at low fields, but level off as the material approaches saturation. Ferromagnetic curves exhibit a sharp initial increase, then plateau once domains are fully aligned, reflecting strong permanent magnetism. Pause 0.8. When two bar magnets are brought close, each develops a north and south pole that generate magnetic fields. The field lines emanate from the north pole, curve around, and re-enter at the south pole, forming closed loops. If like poles face each other, their field lines diverge, creating a region of higher magnetic pressure that pushes the magnets apart. Conversely, when opposite poles approach, the field lines connect smoothly, lowering magnetic pressure and pulling the magnets together. The underlying mechanism is the Lorentz force acting on microscopic moving charges within each magnet's lattice structure. These charges experience a force perpendicular to both their velocity and the local magnetic field, aligning dipoles in a way that produces macroscopic attraction or repulsion. In a simple model, each bar magnet can be represented as a magnetic dipole moment pointing from south to north. The interaction energy between two dipoles depends on the angle between their moments and the distance separating them. When the moments are parallel and aligned head to tail, the potential energy is minimized, leading to stable attraction. If they are anti-parallel or side-by-side with like poles adjacent, the energy increases, causing a repulsive force that pushes them apart. Pause 0.8. When electrons move through a conductor, each segment of the wire generates a tiny magnetic influence that adds up to a measurable field. The Biot Savart law quantifies this effect by relating current magnitude, distance from the wire, and direction via a cross product of velocity and displacement vectors. In practice, we often use a straight wire first. The resulting field circles the wire in concentric loops that follow the right-hand rule. To concentrate these circular lines into a usable north-south pair, we wind the conductor into a coil, which superposes many individual fields. The overlapping loops reinforce one side of the coil while canceling on the opposite side, creating a clear magnetic dipole aligned with the current direction. By powering the coil, the emergent field lines emerge from what becomes the North Pole and re-enter at the South Pole, just like a permanent magnet. The strength of this induced field scales with both the number of turns in the coil and the magnitude of the electric current flowing through it. This principle underlies electromagnets used in cranes, relays, and loudspeakers, where adjustable currents control magnetic force on nearby ferromagnetic materials. In a laboratory setting, one can observe the field by placing iron filings around the coil. They trace the invisible lines predicted by theory. Thus, the simple motion of electrons inside a wire is the fundamental mechanism that turns electricity into magnetism. Pause 0.8. Magnetism is a fundamental force that arises from moving electric charges and intrinsic magnetic moments of particles. In everyday devices, this force is harnessed through carefully engineered magnetic fields to perform useful work. A prime example is the MRI scanner, where strong superconducting magnets generate a uniform field that aligns hydrogen nuclei in the body. When radiofrequency pulses disturb this alignment, the returning signal is detected by receiver coils and translated into detailed images. The same principle of magnetic induction underlies electric motors, which convert electrical energy into mechanical rotation via Lorentz forces on current carrying conductors. Inside a motor, permanent magnets or electromagnets create a rotating field that interacts with copper windings to produce torque. The interaction between magnetic flux and the conductive loops generates an electromotive force that sustains rotation once initiated. Both MRI and motors rely on precise control of field strength, orientation, and timing to achieve efficient operation. In medical imaging, field homogeneity is critical for image clarity, while in motors, field symmetry ensures smooth torque delivery. These applications illustrate how understanding magnetic mechanisms enables the design of complex systems that impact health, transportation, and industry. By studying the underlying physics, engineers can innovate new devices that exploit magnetism for even greater societal benefit. Pause 0.8. Key takeaways. 1. Magnetic fields arise from moving charges and act on other moving charges and dipoles. 2. Electron spin and orbital motion create microscopic magnetic moments. Alignment leads to macroscopic magnetism. 3. Materials respond differently. Diamagnetic repel. Paramagnetic align weakly. Ferromagnetic align strongly. 4. Electric currents produce magnetic fields. Biot Savart law, enabling electromagnets that power motors and medical imaging.